The octopus did not inherit its intelligence. It built it, from scratch, completely alone. 600 million years ago, the ancestor we shared with an octopus had no brain, no eyes, no nervous system worth naming. It was a flat worm pressing itself against the sea floor. That's where our family trees split, and from that worm, two wildly different paths climbed toward complexity. One path became us. The other became something stranger, something that solved every problem we solved, without ever once using our solutions. This is not a story about a smart animal. This is a story about intelligence inventing itself twice, independently, on the same planet, in the same ocean. And what that means is more unsettling than almost anything else in biology. Let's go back to that seafloor. 600 million years ago, the ocean is not empty. It is teeming. Soft bodies, no shells, no bones, things that pulse and drift and flatten themselves into the silt. Among them is a creature so simple it barely registers. Scientists call its rough category the last common ancestor of mollusks and vertebrates. It has no spine, no skull, a rudimentary cluster of nerve cells that does the bare minimum, tells the body to contract, tells the body to release. That's it. That's the brain. That's your great-great-great-grandmother, several million greats removed. That is also the octopuses. From that flatworm, one lineage started doing something radical. It folded its nerve tissue into a tube along its back. That tube became a spinal cord. The spinal cord thickened at one end. That thickening became a brain. Over hundreds of millions of years, fish got that brain, then amphibians, then reptiles, then mammals, then primates, then us. Every vertebrate on this planet is running a version of the same original blueprint, iterated, refined, but recognizably descended. When a crow solves a puzzle, or a dog reads your face, or a chimpanzee uses a stick as a tool, they are using architecture that traces back in an unbroken line to the same common design. The octopus used none of that. The mollusk branch took a different road entirely. Most mollusks kept things simple. Clams, mussels, snails. A modest nervous system scattered in small ganglia throughout the body. No central command, no ambition. The blueprint was conservative. It worked. It survived. It did not push further. But something happened in one particular lineage, the cephalopods, the branch that would become squid, cuttlefish, and the octopus. Something about their situation, their predators, their hunting needs, the arms race of the Cambrian and post-Cambrian seas started pushing their nervous systems forward, hard, fast, in a completely different direction. The octopus today has around 500 million neurons. That is roughly the same count as a dog. But here's where it gets strange. 2/3 of those neurons are not in their brain at all. They are in their arms. Each arm thinks partially on its own. When an octopus reaches into a crevice it cannot see, the arm is making local decisions, tasting, touching, adjusting grip without waiting for central approval. The octopus brain is less a command center and more a coordinator. It sets goals. The arms figure out the details themselves. No vertebrate nervous system works this way, not even close. The octopus did not wire intelligence into a central brain the way we did. It distributed it, spread it across its body like a network. A completely different architecture producing a completely comparable result. And the results are genuinely comparable. This is not metaphor. Octopuses open child-proof jars. They unscrew lids from the inside of tanks. They escape enclosures that engineers designed specifically to hold them. At the Middlemore Hospital in New Zealand, an octopus named Inky slipped through a small gap in his tank lid, crossed the floor, and disappeared down a drainpipe to the ocean. He did not panic. He assessed. He moved. He left. Researchers at the Seattle Aquarium documented octopuses shooting jets of water at overhead lights they found annoying, repeatedly, until staff dimmed them. That is not reflex. That is a complaint. That is cause and effect, understood and acted upon deliberately. They play. They have been documented interacting with objects that have no food value and no survival function, for no apparent reason other than engagement with the object itself. They recognize individual human faces and respond differently to different people. In controlled experiments, they watch other octopuses perform tasks and then replicate the solution faster than those who had to figure it out from zero. Observation, imitation, social learning. Things we associate with mammals, with the so-called pinnacle of vertebrate cognition. But the octopus is not a vertebrate, it is a mollusk. It is more closely related to a clam than it is to a crow. And yet. Here's the part that scientists find almost philosophically uncomfortable. When you look inside the octopus brain and compare it to a vertebrate brain, they do not look the same. Of course they don't. But more than that, the specific structures that vertebrates use for learning, for memory, for decision-making, do not exist in the octopus. The hippocampus, gone. The cortex, absent. The entire scaffolding that vertebrate intelligence is built on, simply not there. Instead, the octopus has its own structures, its own lobes, its own organization, named differently because they are different. They evolved separately, and somehow, running on completely alien hardware, the octopus arrived at outputs that look remarkably like ours. This is what biologists call convergent evolution. When two lineages, separated by hundreds of millions of years, independently arrive at the same solution to the same problem. Eyes evolved at least 40 times in different animal lineages, all solving the problem of detecting light. Wings evolved independently in birds, bats, and insects. But intelligence, genuine, flexible, problem-solving intelligence that was supposed to be rare, maybe unique. Convergent intelligence at this scale, between two lineages as distant as an octopus and a human, is one of the most extraordinary examples the natural world has produced. And the separation really is that vast. When scientists mapped the divergence point using molecular clocks, looking at how DNA accumulates, changes at a measurable rate over time, they placed the split between the cephalopod lineage and the vertebrate lineage at somewhere between 550 and 600 million years ago, before the Cambrian explosion fully unfolded, before fish, before anything with a spine had entered the fossil record. The common ancestor they traced back to was, by any reasonable standard, brainless. The octopus had no head start, no borrowed designs, no shared inheritance of complexity to build on. It looked at the same ocean full of predators and prey that vertebrates would eventually look at, and it engineered its own answer. There is one more layer to this that stops researchers cold. The octopus lifespan is brutally short. Most species live 1 to 2 years. Some larger species reach 4 or 5. They do not have extended childhoods where they learn from parents over years the way primates do. Most octopuses never meet their parents at all. The mother dies guarding her eggs, the young hatch and disperse immediately. Every octopus is essentially self-taught. All of that intelligence, that flexibility, that capacity for learning and problem-solving and tool use compressed into 2 years, built from almost nothing, almost alone, almost instantly on the scale of a life, and then gone. What drives that evolution if not extended learning time? The pressure of hunting, the vulnerability of a soft body with no shell in an ocean full of things that want to eat it. Speed, camouflage, and cleverness became the only armor available. The octopus cannot outrun a shark. It cannot outmuscle a moray eel. What it can do is think faster, hide better, and find solutions that its predators have not anticipated. Intelligence was not a luxury for the cephalopod lineage. It was the survival strategy itself. The arms race of the sea played out not in teeth and armor, but in neurons. So when you watch an octopus unscrew a jar, when you see it change color and texture in under a second to vanish against a reef, when you see it squeeze its entire body through an opening the size of a coin because its only rigid structure is a tiny beak, when it looks at you with that strange rectangular pupil and you feel, briefly, that something is looking back, something that actually sees you, you are not imagining it. You are right. Something is in there. Something that took a completely different road from ours and arrived at awareness anyway. Something that built a mind out of materials and methods that evolution never handed to us, in a body that evolution never handed to us, in a timeline that evolution barely gave it. The octopus did not learn from us. It did not borrow from us. It did not evolve alongside us or benefit from any shared heritage of growing complexity. It started from the same flat worm we did. It went the other direction, and it got there anyway. Intelligence, it turns out, is not one thing that happened once. It is a destination, and more than one path leads there.